Unit 1, General Physics. We speak about speed, velocity measurements, acceleration, moment, momentum, work, energy. Unit 2, Thermal Physics. We speak in this unit about the temperature, thermometers, the heat energy, how we can measure energy. Is the temperature is hot or cold? We know the new meaning of the temperature and what is the difference between melting, boiling, evaporation, vaporization. In Unit 3, nuclear physics. In this unit, we are speaking about the atom, nucleus, radioactive elements, how we can measure the reactivity of or activity of these radioactive elements, and what is the half lifetime of these. And in Unit 4, we have electricity and magnetism. What is the electric current? What are the magnets? How the magnets attract and repel? Can I change the magnetic field to electric field? Can I change the electric field to magnetic field? And some different applications and devices like motors, generators. And finally, in Unit 5, waves. We have longitudinal waves, the transverse wave. What is the difference between them? What is the nature of light, visible light, electromagnetic spectrum? You know, we have the rainbow, 7 colors come from the sun. We see only the white light, but we can see rainbow when it's rainy. And also, we speak in this unit about lenses, convex lenses, and the mirrors. And as you know, in your exam for Cambridge, you have 3 papers: paper 2, 4, and 6. 2 multiple choice, and 4 is a theory paper, and the paper 6 is the practical. And then in the Excel, we have only 2 papers, 1P and 2P. The 2 papers are mixed between the multiple choice questions and the essay questions. But in the Excel curriculum, we have also one more unit. It's the space. We speak about the space, the moons, and the planets. But it also is introduction in the space science, not in details. Okay, today I pick an interesting topic in the Unit 1, General Physics, which is moment or turning force. When I have an object and this object it changes its position, we say there is a displacement, or this is or a change in the position. I can measure the distance to see this. Let's say draw something to make it easy for you. I have an object and this object in position A, and then it changes the position to be in position B. If I have an object in position A and then it changes its position to position B, so this is distance or displacement. I measure the distance between A and B, the distance. Okay, this is the changing in position. We call this displacing. But if I have something and this thing is turning It's make a rotation. Like when you open the window or you open the door does not change its position. The door in the same position, but the point is that the door is rotating about fixed point. And also, when you open the physics book, you open the cover and then first page, second page, and so on. You make turning effect for the paper of your physics book. These papers don't change its position. This turning effect called moment. And this is the name of our topic today, turning forces. If a body is fixed at a certain point, called pivot or fulcrum, this is the point where the object rotates. We can call it pivot or fulcrum. A force applied to the body can cause rotation about the pivot without displacing the body. As I told you, the cover of the physics book make only rotation. Okay, so how we can write this formula? We can write by this way. Moment equal force by perpendicular distance. So F represents for force and D for the perpendicular distance. This is the vertical distance or normal distance. The measuring unit for force is Newton. The measuring unit for distance is meter. No. In moment, we only have one pivot. Okay, so the measuring unit here is Newton meter. Now the question, moment is a scalar or vector? You can write on the chat box. Good Abdo, good Asim. Okay, moment is a vector quantity which has magnitude and direction. But what is the direction of moment? Moment has two directions, clockwise or anti-clockwise. If I want to get a larger moment, what I should do? We can apply larger force because when the force increases, moment increases. And I can increase the distance, perpendicular distance. And here the distance is the distance between the pivot and between the applied force. Let's see, this is the pivot or fulcrum, a small triangle represented by a small triangle. This is the force and this is the pivot. So this distance is perpendicular distance between the force and the pivot. So when I make multiplication for this force by perpendicular distance between force and the pivot, this is the moment. And its measuring unit, Newton meter. And as we said, moment is a vector quantity which has magnitude and direction, and the directions are clockwise and anti-clockwise moments. Let's take some examples for moment. When you're holding a bar with weight hanging from it, it becomes more difficult to hold it if the weight is moved away from your hand. See the weight, you can hold it easily, but if this weight at the end of the rod, it will be more difficult to hold this weight. You will apply more force.
If it
Another,
goes right, it will become even more difficult.
yes, More difficult due to you will apply more force, so you have more moment. In the next example, undoing a nut by a spanner. Here we have a nut, and we wanted to make undoing for the the nut by spanner. So it's better to have a longer one. Why? Due to when the distance increases, so you make a smaller force. See here in our board, force and distance are inversely proportional. This means when the force decreases, distance increases. So when I want to apply a smaller force, I can increase the distance. That's what happened here in this example. The spanner is longer, so I make a smaller force. The moment here is clockwise. The next example, opening or closing a door. This is better to be done as far as possible from the hinges of the door. See, this is the bodybuilder and this is a thin person or a thin man. What happened here? The thin man wanted to push the door, so the door opened in his direction. But the bodybuilder person, no, he wanted to close the door, but he can't. Due to he go nearer to the pivot. That's why he need to make much more force. When you're pedaling a bicycle, this is long pedal, so you make a smaller force. Also, when you open a cap of a bottle, or you if the cap is larger, you make a smaller force. If the cap is smaller, you make larger force. Now the question for you. Here in the shown figure, try again, guys. Try again. We take the force and the perpendicular distance. Which choice gives the anti-clockwise moment? About O. This is O point. Here we have a rod. Its distance is 5 meters, and this is force is 10 Newton. And also we have 3 meters and 4 meters distances. I want you to tell me the moment. You can write in the chat box. One of you send the answer. Okay. Okay, guys, here the answer will be 10 by 4, it will be 40. Due to 10 is the force in Newton and the 4 is the perpendicular distance between the force and between the pivot. When I speak about moment, there is an important conditions for equilibrium. I want to make equilibrium. That's why we study moment. So, if a body is in equilibrium under the action of several forces, it must satisfy two conditions. I cannot see the body in equilibrium. I can say that in only if two conditions apply. First one, no resultant force in any direction. This means the sum of forces in any direction must be equal to the sum of forces in the opposite direction. And also no resultant moment in any direction. This means the total clockwise moments equal the total anti-clockwise moments. What does it mean? See, here we have two persons. This is the children and this is the big man. Okay, and the big man has a heavy weight, but the children has a small weight. So uh, now they are in equilibrium. How? By two conditions. First, no resultant force in any direction. This means the forces, downward forces, equal the upward forces. So here I have the weight of the children and the weight of the man, W1 and W2. do downward forces, and where is the upward force? The one comes out of the pivot. So the downward forces must equal the upward forces. You can see it here more clearly. Here 10 Newton and 6 Newton. 10 plus 6, 16. So the force here, upward force is 16. So the downward forces equal the upward forces. And also no resultant moment in any direction. And this means the total clockwise moments equal the total anti-clockwise moments. So here we have the first weight of the heavy man, it will be W, capital. And the distance D small, due to the big man nearer to the pivot. And next, the children have W small because he has small weight. And the distance is lower, so he has D capital. So both are equal, both moments are equal. The children make clockwise moment, and big man make anti-clockwise moment. So the clockwise moment equal the anti-clockwise moment. That's why that the big man who has a heavy weight and the children who has small weight, they are in equilibrium. Let's apply the equilibrium again in the next example. Here we have two forces, 10 Newton and 6 Newton, and we have two forces, two distances, 3 meters and 5 meters. So let's apply the first condition. No resultant force in any direction. The upward force from the support must equal to 6 plus 10. Why? Due to, I told you before, the total or the downward forces must equal the upward forces. That's why I make addition 6 newtons plus 10 newtons, so it will be 16 newtons. So the first condition apply. Next one, no resultant moment in any direction. Let's see the clockwise moment and the anti-clockwise moment. For clockwise moment, this one, 10 Newton. See, clockwise moment. So force by perpendicular distance. Where is force? 10 Newton. Where is perpendicular distance? 0.3 meters. So 10 by 0.3 meters, 3 Newton meters. This is the clockwise moment. Let's see the anti-clockwise moment. 6 Newton by 0.5. So the answer 3 Newtons meter. 3 and 3. So clockwise moment equal the total anti-clockwise moment. So the two objects here are in equilibrium. When we speak about equilibrium, we have to see one important scientific term, which is center of mass or center of gravity. Here, the center of gravity is the point through which the whole weight of the object seems to act. See this table, where is the center of gravity or center of mass? In this point in the middle, and the pencil, this is the center of gravity. This is the point through which whole weight of the object seems to act. If we have a regular object, so let's take example. If we have flat card, what we are going to do? First, you have to put the object. You hang this flat card, let it hang freely, and put this line called plumb line, and let it hang freely also. And then mark the line with a pencil. This is the first step. Next step, flipping the cord, and then let the cord hang freely, and also hang the plumb line freely also. You can draw a line, and then you flip the cord again, hang it freely, and the plumb line hang it again, and mark the plumb line on the cord. So you have many lines intersect together in one point. This point is the point of center of mass or center of gravity. But we know when you make an experiment, you have to repeat more than 7 times to and then get the average to reach to the accurate answer or to the accurate results. When you do an experiment to verify the principle of moment, which says no resultant force and no resultant moment in any direction, there is some points you have to put in your consideration. First, put a meter rule on a pivot and try to balance without any weight. Then mark the position of the pivot on the meter rule. This is the position of the center of the mass of the meter rule. So now, ruler without any weight, I know the center of mass. And then try to put different masses in different position till the meter rule be balanced. And try to put different rules, weights in different distances, and then put this in tables. So you have a clockwise moment and anti-clockwise moment. And from this table, you can get the moment, or you can make the conclusion of the principle of moment, how to make the object in equilibrium. The last concept related to the moment is stability. So we took moment, conditions of equilibrium, center of mass or center of gravity, and finally stability. So some things topple over more easily than others. When the glass stands vertically, the weight vector passes through the origin, or sorry, through the base. See, this is the base of the tall glass. This is the arrow is weight vector. So when the weight vector passes through the base, this means the glass stands vertically. That doesn't topple over. So in the first case, the tall glass is standing vertically and the glass is stable. The next figure, when the glass is pushed a little, the weight vector is still passing through the base. See, weight vector also passing through the base. It turns back to its original position. The position of the glass was stable. The last one, if the glass is pushed much further, so it topples. It starts to topple when weight vector passes over the edge of its base. So to make the objects more stable, the weight vector must pass through the base. Now the question, how the stability of the body can be increased? We can increase the stability by having a larger base area, this base area, or having low center of gravity. The mean make this part lower. You can try this in your home. In moment we have some problems and we have some techniques to answer or to solve these problems. First, it's very difficult to balance a meter rule on a pivot as it's the center of mass. It's a problem. So the rule usually tilts in one direction. So the position of the center of mass is difficult to determine. So what is the solution? And even you have rulers, but they are 30 centimeters. So the center of mass at 15 centimeters. But when you put it and try to make it in equilibrium, you see or you find the center of mass at 15.5 centimeters. It's a problem. How you can solve it? Try to repeat balancing and mark the closest position of the center of mass several times. As the rule approaches balancing, then get an average of all these positions. So I repeat more and more and put the pivot and try to balance the ruler till I get the most accurate point. Another problem, as the meter rule may not be perfectly uniform. So the position of center of mass is not exactly at 50 centimeters mark. If you have a meter rule, its length is the 100 centimeters. So if it's a standard, so the center of mass must be 50 centimeters. But if it's not standard or it's not uniform, so it will be not at 50 centimeters. So you can make two solutions. The first, put the pivot at the 50 centimeter mark and add a piece of plasticine where at the lighter end of the meter rule till it becomes balanced. So you have the two ends of the ruler balanced, horizontal. Next, balance the meter rule on the pivot at any point and make all distance measurements from this point. This means you put the meter rule on the pivot and see where is the center of mass. It will be 50.5, 51 centimeter, and you try to put different weights and take the equilibrium state at this condition. The last problem, the masses hanging to the meter rule may slide as the rule tilts a little. How I stick the masses or put make the masses stable on the meter rule. Try to repeat hanging of masses and mark the close positions of masses several times. As the rule approaches balancing, then get an average of all of these positions. So I put my the ruler and put the pivot and they put my masses and try to put them without sliding or tilting left or right to make a balancing and to apply the conditions of equilibrium. So that's all for moment. Yeah, thanks a lot for this session and so happy to having me with the Rosita Academy, and I hope all of you the best in your life. Goodbye.